What we are looking at is Theorem 6.2. Which is, if one side of a triangle is longer than a second side, then the angle that's opposite the longer side will be larger than the angle that's opposite the shorter side. So, if one side of a triangle is longer than a second side, then the angle opposite the longer side will be larger than the angle opposite the shorter side. So in our diagram, we are going to have a triangle with one side obviously longer than another side. And so we're going to work with, in this triangle, triangle RST. And we are going to know that RT is greater than RS. What we are going to prove then is that the angle opposite this longer side, now this is our longer side, the angle that's opposite is this angle S, yes. So we have to prove that that angle is larger than the angle that's opposite the shorter side. This is our shorter side, so the angle opposite it would be angle T. Now, because we're going to draw in our proof a line that goes through angle S, we'll have to refer to that as angle RST is greater than angle T. And we're talking measure of angle, so I should have a little m there. All right. Now, since RT is longer than RS, there, by the ruler postulate, we can find a point Z that makes RS and RZ congruent. So that's the first step of our proof. Locate point Z so that on segment RT so that RZ equals RS. The next proof we do will be an indirect one. This one is a direct one. So we're going to locate point Z on segment RT so that RZ equals RS. Now what we're going to do is draw a segment from Z to S, forming an isosceles triangle. That segment cuts this angle into two pieces. We'll call them piece 1 and piece 2. So we have angle 1 and angle 2. We're going to call this other angle that's equal to angle 2, because they're base angles in an isosceles triangle, angle 3. So first off, I know that angle RST is greater than angle 2. Why do I know that angle RST is greater than angle 2? Exactly. That's the last property of inequality, isn't it? Because RST is equal to the sum of angle 2 and angle 1. Angle RST has to be larger than either of those angles singly. So angle RST in measure is greater than angle 2, which really means that angle RST is also greater than angle 3, because this is an isosceles triangle. Angle 2 equals angle 3. So our next statement is, since angle 2 is equal to angle 3 by theorem 4.1. Then we can say that measure of angle RST is greater than measure of angle 3. Now, I know that angle 3 is an exterior angle of triangle TZS. If you look at this triangle right here, angle 3 is the exterior angle of that triangle. The exterior angle inequality theorem, theorem 6.1, says that since that angle is the sum of these two angles, it must be larger than either one of them. So angle 3 is larger than angle T. Angle 3 is also larger than angle 1, but we want angle 3 larger than angle T. So by theorem 6.1, which is your exterior angle inequality theorem, and says that the exterior angle of a triangle is larger than either of those remote interior angles. Measure of angle 3 is greater than measure of angle T. Now we can put these two pieces together. You see how you have that angle RST is greater than angle 3, and then you have that angle 3 is greater than angle T? If we put those pieces together by a property of inequality, it's actually the one we call the transitive property of inequality. Since RST is bigger than 3 and 3 is bigger than T, then measure of angle RST is larger than measure of angle T. Thread. And we'll say by the transitive property of inequality. That is what we wanted to prove. And we did it. That was actually easy. All right. So on theorem 6.3, we get to use an indirect proof because we have this theorem to contradict. So on theorem 6.3, it's kind of the converse of this, which allows us to use an indirect proof and lead to a contradiction of this. Okay, so theorem 6.3 says if one angle of a triangle is larger than a second angle, then the side that's opposite the first angle will be longer than the side that's opposite the second angle. Okay, let me make a correction already to my notes. I have one angle is longer. We don't say that, we say one angle is larger, right? Let me make that correction.
That's what the book said.
Well,
the book said larger.
Larger, yeah. But I put longer. So if one angle of a triangle is larger than the second angle, then the side opposite the first angle will be longer. So here we need to draw a diagram that has one angle obviously larger than a second angle. And we can go ahead and work with our same triangle RST here. What we're going to be given in this case is that angle R is larger, well, let's do angle S is larger than angle T.
Angle F.
Maybe, maybe not. What we want to prove then is that the side opposite the larger angle, since angle S is a larger angle, the side opposite is this side. Since angle T is the smaller angle, the side opposite is this side. So what we want to prove is that segment RT then has to be longer than segment RS. Since we're going to do an indirect proof here, what will we start by assuming?
That RT is greater. RT is less than.
Or equal to, right? We start by assuming the opposite of what we want to prove, and the opposite of greater than is less than or equal to. So assume temporarily is where we start. Assume temporarily that RT is less than or equal to RS. Now we actually have two cases here, less than or equal to. So if RT equals RS, what will happen? If RT and RS are congruent, what will happen? If these two sides are congruent, then it's an isosceles triangle, right? What do we know about an isosceles triangle? They have congruent base angles. These angles opposite the congruent sides are equal. So then angle T will equal angle S. We'll put measure of angle T and measure of angle S, because it is an isosceles triangle. Now the second piece. If RT is greater than RS, yes, thank you. If RT is less than RS. Because we're assuming less than or equal to. Well, let's talk about it. Instead of them being equal now, we have actually that RT is the shorter side. So what does Theorem 6.2 say if this is the shorter side about that angle? That it has to be smaller, right? So angle S, which is opposite the shorter side, must be smaller than, and the longer side then would be RS. So here is RS, the angle opposite that is angle T. So measure of angle S is less than measure of angle T. And this is by Theorem 6.2, the one we just looked at. In both cases here, do we have a contradiction to the given? Yes, because measure of angle S is not equal to measure of angle T, and measure of angle S is not less than angle T. So here we start the conclusion of our paragraph, or of our indirect proof. There we are. So we're going to say, in both cases, we contradict the given information that measure of angle S is greater than measure of angle T. So we have the first statement. The second statement will be, this means what we assumed is incorrect. And we put in there what we assumed. What we assumed that RT is less than RS. Is incorrect, and instead and now we put in what we want to prove. RT is greater than RS. Now we have two corollaries to Theorem 6.3. Corollary 1 says the perpendicular segment from a point to a line is the shortest segment that can be drawn from that point to the line. So this is corollary 1 of Theorem 6.3. So in our diagram then, let me start with a point, I guess. We have a point and a line. And we're going to be looking at a perpendicular segment drawn from that point to that line. So we have a point P. This perpendicular segment is going to intersect that line at, let's call it a point X. And we have a line L. And we're going to look at any other segment drawn from that point to the line and prove that PX has to be shorter than any other segment that's drawn from that point to that line. So here we have another segment drawn from that point to the line. We'll call this point right here Y. And our given information is basically the diagram shown. And what we want to prove is that PX is less than PY. Now we're using Theorem 6.3, which says if one angle of a triangle is larger than another angle, then the side that's opposite the larger angle has to be longer. In this triangle here, PXY, what is the largest angle? This measure of angle X, right? It has to be 90, and the others have to be acute, or less than 90, because there can be at most one right angle in a triangle. So really the reason behind this is since measure of angle PXY is greater than the measure of angle, and here I want the angle that's opposite segment PX, which would be angle PYX. And then what I know is if this is a larger angle, PXY is a larger angle, then the side that's opposite has to be longer. Thank you. Then the side that's opposite the smaller angle. So this is telling me then that PY has to be longer than PX. Or, in other words, that PX has to be shorter than PY. Corollaries are usually just one step more than a proof. That's why they're called a corollary. They're just kind of a sub-theorem. They're a direct result of another theorem. Corollary 2 now says the perpendicular segment from a point to a plane is the shortest segment from the point to the plane. It is the same statement as corollary 1, but using 3 dimension. So corollary 2, a perpendicular segment from a point to a plane is the shortest segment from the point to the plane. So here we have a point, we have a plane we can draw a parallelogram to kind of represent. It is. A perpendicular segment now from the point to the plane. In order for a line to be drawn perpendicular to a plane, it will be drawn perpendicular to every line that is on the plane. So if there was more than one line here, in order for that to be drawn perpendicularly, it would have to be perpendicular to both of those lines in the plane. So we have then right angles formed between this segment and every line that goes through the point of intersection of that segment in the plane. So if we call this point P and that intersection with the plane X, and if we draw another segment that goes from that point to the plane, call it PY, we can basically use the same proof that we used on corollary 1. So our given is going to be the diagram. At 54 is late lunch, early lunch is 50.
We're early.
We should be early today. So what we want to prove here is that Px is less than Py. And what I'm going to write for a proof is see the proof for corollary 1.
Where is that? Oh.
So the last theorem here is theorem 6.4. Which is the triangle inequality theorem. And what this theorem says is the sum of the lengths of any two sides of a triangle will be greater than the length of the third side of the triangle. Now, what we are going to work with is a triangle where we know that one of the sides is longer than the other two, or else the same length as the other two. Because if you work with a triangle, you know that either all three sides are the same length, or there is one side that will be longer than the other two. So that's what we're going to do with segment AC here. We are going to be given that AC is greater than or equal to the other two sides. Because that will always be the case. You'll have one side that is either the same length as the other two or the longer. So AC is that side. It's either bigger than or equal to the other two sides. What we want to prove is actually three pieces. We want to prove that if I add AB and AC, it will be longer than BC. We also want to prove that if we add BC and AC, it'll be longer than AB. And finally, we want to prove if we add the two shorter sides here, AB and BC, that that will be longer than AC. These first two are a property of inequality. Take a look at them with me. Because AC itself is larger than or equal to BC, and because neither of these other two sides are equal to 0, AB and BC are not a zero measure, then if I take AC plus something else that's non-zero, then this value has to be larger than BC because AC is larger than BC. Same thing here. If I take AC plus another value that's bigger than 0, since AC itself is bigger than AB, then AC plus this value that's larger than 0 has to be larger than AB. So both of these are a direct result of a property of inequality. So these are properties of inequality. The proof of this third one will come from if we draw a perpendicular segment from B to AC. Call this point X. Then what we know is that segment BC has to be longer than segment XC. And segment AB has to be longer than segment AX. So tell me what would happen if I add these together. I get AB plus BC is greater than AX plus XC. And what is AX plus XC? That's AC, isn't it? So that's how the proof is going to go for the third part. These two segments here added will be larger than that long segment.